Okay, great. Good morning and welcome everyone to this day on Quantum Meets AI. So this is, well, let me just say a little bit about what the day is supposed to accomplish. You know, there's been, of course, a lot of excitement and interest and maybe even anxiety about what AI is going to bring to science and math and theoretical computer science. And so, you know, the thought behind this day was that you know, the best way to deal with all this is to really understand the facts on the ground. And so what the day features is talks about one, accounts of research that has been heavily inspired by AI, and you know, also saying how, you know, what role did AI play in that research and actually doing those proofs, but also in rather bigger aspects, you know, such as in what ways does AI actually change the agenda within certain fields, and also how it changes the ambition of projects or companies, etc. So that's what this you know, today's going to feature. So the first talk is a case in point. It's really a great pleasure that Matthias is here from Microsoft. He, as you might know, he's a technical fellow and corporate vice president of Quantum at Microsoft. He's thought long and deep about you know, about quantum chemistry and resource estimates for quantum chemistry long before, you know, almost anybody was really taking that so seriously. His 2023 paper on disentangling hype from practicality, I think this was a really notable paper. I think Matthias talked about it in our quantum colloquium, and that was something quite memorable. And his more recent work on teaching quantum physics to AI, yeah. I think this has been, I found it very eye-catching, you know, when I heard him give a talk about it a month or so ago. Mm-hmm. Matthias, real pleasure. And
thank you.
Looking forward to your talk.
Thank you, and it's nice to be back here. The last decade I've been here mostly for marine ecology, not quantum, so it's nice to also be in town for quantum computing again. And let's say, where did this whole interest start? It started back 25 years ago. My colleague, Johnny Platter, asked me, what do you know about quantum computing? I said, I don't know much about it. He said, but could you help us simulate the topological qubit? And that was my first Nature paper in that field. But then it was basically just the experiments in condensed matter physics. What device could you build that is a two-level system? And then I applied at that time also for a faculty job in computer science, because they asked me to apply, but then told me, look, it's strange, quantum computing is two totally distinct communities. There are experimental physicists making devices that have two-level systems, and there are information theorists proving theorems, then computer science, but there's no connection between the two. And then I fast forward the decade, to 2011, D-Wave built a machine and said, quantum has arrived, we have 128 qubits. And people asked, what is this about? And so we investigated it and found, hey, it's an interesting quantum device without any quantum speed up. Then people asked, how can it be? How can it not be faster than classically? It's quantum after all. And they say, yeah, quantum computing just has the potential for quantum speed up, but for certain operations, it's not. And for certain applications, there's what we then termed quantum slowdown. But that's when then we said, kind of look, where are the real applications for quantum computing? That's what Mike Friedman asked me back then, Fields medalist, leading the the quantum program then. Where are the applications? So we started to look at rough estimates for what could the applications be. In Grover for database search, it quickly turned out, well, if for every Oracle call I have to load the full database, then that will not work. So we worked through it and started looking for application of quantum computing. And then some colleagues told me, Matthias, you're mad. You're doing applied quantum computing. You think this thing is real? And I said, yeah. I mean, if we invest in it, in research or in a company, then we better think about what is the application really. And it's not just science fiction, but we started out doing resource estimation for a science fiction-ish quantum computer. What could I do if my logical cycle time was 1 nanosecond? Because that's not impossible from physics. And then we already ruled out many applications that are mostly linear I/O bounded, so that science fiction approach made sense. Over time, it became more realistic. And then in 2016, I started working also on the machine learning for quantum systems because my postdoc said he wants to train an ML model to find a ground state of a quantum system. He told me, look, we have the best classical algorithm, the best variation wave functions. ML will not do better. And of course, I was proven wrong. So, and then when I moved to Microsoft, my only regret was that now I'm leaving that field of machine learning and AI for quantum. But it wasn't long until we realized that is merging again. So why did I move from academia, from a well-paid faculty job that is well-funded? Because at ETH, I had a base funding of 600,000 Swiss francs per year to hire postdocs or students without the grant proposal, just some venture capital to invest in new lines of research. That was great. So why was I so crazy to leave that? It was because at that time, most of my funding came from the US, and most of my funding beyond all the big grants I had came from Microsoft, came from IARPA, for really quantum engineering, for building software, for building machines. And that didn't work well in academia, but that's where, with the company, I could actually realize that. So then my focus has shifted over the last years more and more from being an academic to being an executive, which is what I never expected I'll ever be. But it's still the same because we're still doing R&D, we're still building new machines, we're building amazing devices, and we drive the research forward in a mission-focused way. Because we want to build those devices, and we need to ultimately make money. And so we've been thinking about where is the application. So when we think about it, the new thing about quantum computing is the new technologies have always advanced computing, but not the way we compute. The fastest GPUs works on the same principle as the abacus, just digital classical logic. There's been no change in the way how we compute. We just made it faster by a factor quintillion and more. Until quantum computing arrived. With that, for the first time in millennia, we have a new way of computing. And with that, there's lots of hype around it. But that hype slowly starts to give rise to clarity of what quantum computers will be good for, and what they will not be good for, and clarity of what it will need to get there. And when people ask me, what is the single one thing that slows down our progress, then my recent answer was, it is that quantum scientists like to keep quantum mysterious. There's this spooky action at distance, it's so hard and so complex and so on. And that really slows us down as we try to build it because it scares away people. But it also attracts lots of hype because quantum is this mysterious thing that can solve any problem. So quantum has become the new God in the gaps. I have an optimization problem, I have this problem and that problem that I don't know how to solve, so let me go to quantum. Once there was somebody from the UN agency tell me they need quantum because for crop rotation in the global south with climate change, they don't understand the science, they don't have the data, they know nothing, so they need a quantum computer to solve the problem for them. that just shows where this quantum hype goes. But it's slowly being replaced now these days by the Clarity. And the Clarity came also from DARPA asking us, what is a utility scale quantum computer? And when they first asked me years ago, they said, for me, utility scale for quantum computer is that I can build a quantum computer that can solve an interesting science problem that they would not have been able to solve classically. The classically intractable problem that they can solve. DARPA then pushed back and said, Matthias, that's not enough. And there are people, I know, that think I'm the quantum pessimist. I'm the one who started talking about millions of qubits. And then DARPA came back to me and said, Matthias, you're far optimistic. The real resources you need are at least 5 orders of magnitude more than you think. So that was the first time I was called the quantum optimist. Because their point really is, utility scale for them is solving a problem where the value of the solution exceeds the cost. That seems very business-oriented. And when they asked me first, what does it cost to run a shot on a future quantum computer, I said, I don't know, and how should I know? But as we think about that, thinking about cost really brings all of the resource requirements down to a simple thing. And chemists also told me, look, if a quantum computation of a chemistry problem costs $1 million or $100,000, nobody will ever use it, will not have any impact. But if it costs $1,000, hey, then I'm going to use it in every single paper for every single calculation to validate it. So cost is an important aspect to it. And then when we looked at problems, which problems are realistic, which problems start to fail, then I had the question, can we get some guiding principle? And that is the paper that Umesh referred to, said, can we find some guiding principle that helps us find the area where solutions are most interesting, where it might be utility scale? So if it costs us $1 billion to build a quantum computer, then we better find a problem that's worth more than $1 billion, that's worth tens of billions, or I better invest $1 billion into other types of research. So now they all know quantum computers will be useful because of quantum speedup, better scaling with problem size. But when we then looked at the first problems, then it's looked more and more to us that, like I've read about it before in a novel that talked about a machine, Deep Thought, calculating the number 42 in 7.5 million years. But the runtimes were more than the billions of years. So what that points to just is the importance of constant. Scaling is important, but if we want to talk about utility scale, about real practical impact, then constants matter, and we all know that. But constants are always what is hard to get, right? Scaling is easier to prove. But we want the constant so that the cost over time is not more than a few days or weeks. I don't want to wait 3 years for the result of my calculation. So, and the reason why it's important is that a quantum operation is intrinsically more complex than a classical transistor switch. So when I'm doing a few operations, then classical will always win. And then with quantum speedup, at some point, quantum will asymptotically always. To be practical, the cost over time has to be small enough. Now, where do we get the constants for future quantum computers that we'll build in 5 years? That's where we then said, let's be the quantum optimist. On the classical side, let's take a single current GPU. And that's an updated version from the paper. So let's take a single one of a recent GPU that's been out for a year. A single one, not the tens of thousands in data centers that you're building, but a single one. And let's assume no improvement over the next 10 years. And the quantum side, now let me speculate, what would I love to have? I would love to have a machine with 10,000 logical qubits and 10 microsecond logical cycle times. That means the physical cycle times of sub-microseconds. A really fast machine, a big machine, all-to-all connectivity. What could I do on that machine? And then the first point to look at is I/O bandwidth. The GPU can load 38,000 gigabit a second, and that's a problem because for big data that is far too slow. I have a problem with loading data for classical computing. So the 38,000 gigabit a second is the problem. It is too slow for loading petabyte-sized data sets. But in the quantum computer, if you have 10,000 qubits and can do 100,000 operations per qubit per second, the 10 microsecond cycle time, then 100,000 times 10,000 is a billion. Can load at most gigabit a second. I/O is a bigger problem quantumly than classically. When I then go that I want to implement an operation like a floating point operation in 16 bits, the GPU can do 2 petaflops, 2 times 10 to the 15 operations per second. Amazing numbers. The Cray computer used in the 90s was in the megaflop scale, so these machines are really amazing. But the quantum computer, with those number of qubits, if I implement the multiply unit, I get to about 10 kiloflops. So see a factor of 11 orders of magnitude difference, 10 to the 4 versus 10 to the 15. And it's the same when you look at the Toffler gate, the logical gate, or other things. It's about 10 orders of magnitude to the 11 orders of magnitude difference. And that is the optimistic quantum chip against the GPU. And then people ask me, Matthias, how can that be the case? How can we get to such a big number? Is that fundamental, or does it just mean that there are big advances to be made? And yes, we can make big advances on both sides. Maybe a bit more quantumly. But where does this big number come from? One is the clock speed. We can switch a transistor in 10 picoseconds. The clock speed of gigahertz is just to synchronize the circuits. In each time step, I'm doing tens of gates, doing a circuit of a depth of tens of gates. And then the clock speed is 10 gigahertz versus 100 kilohertz. There's a factor of 10 to the 5, so it's a factor of 10 to the 6 just in the speed. And then there's the space overhead of QEC, factor 1,000 or so maybe. So that gets us roughly to the number. But even more, when you look at what is all of the classical compute, the signal processing I need to measure my qubits, control them, then I'm easily switching 1 million transistors per physical qubit operation. I'm easily switching 10 to the 11, 10 to the 12 transistors per logical qubit operation. So that's the constant. So now, how do we make the quantum computer win? How does the quantum computer win if I/O is much slower? Okay, simply we look at small data problems. Don't look at big data. The wave function might be able to store big data sets, but getting the data in will be the challenge. And then for compute, we need huge quantum speed up, ideally super polynomial quantum speed up. When you look at that and you want to make up a factor 10 to the 11 with a quadratic speed up, you need a problem where you do 10 to the 22 classical oracle calls. That takes a year. If you do a single operation in the oracles. So we need something with more than quadratic speed up. Quartic speed up becomes interesting. That's why I love those methods. But ideally, the applications we know of all the maze of problems, from protein folding to weather prediction, stock market, big data. So what really remains are problems with super polynomial quantum speedup, small data, cryptanalysis, Shor's algorithm, and simulating quantum systems. Chemistry, material science, pharma. We need more quantum algorithms with a quartic speedup or an exponential speedup. So I'd love you to actually help us find more. That then work on small data problems so that we can find more applications. Having said that, when I then told my team the application of quantum computing will be in chemistry, material science, somebody replied, hey, Matthias, I joined the quantum team because I wanted to change the world. And now you tell me all it's good for is chemistry. That's when I said, look, 96% of all manufactured goods are based on chemistry and material science. If you want to impact something in the world, You do it actually through physical things, through making physical things. And if quantum can help us in how we make things, that is the biggest impact we can have. We talked historically about the Stone Age and the Bronze Age and the Iron Age and the Steel Age. So materials define human progress. So really, if we have a way now to really change the way we do material science and chemistry, then there's no bigger impact one can have. But we'll not get that just purely with quantum computers. We'll get it, as I show, by combining quantum computing with AI and supercomputing. And so let me show you what we did in the past years already, just using AI in HPC, and I show you where quantum comes in. We've trained the AI models in the past for material science, for the forces, and properties, and band gaps of materials. And then we published a paper years back on that model. And then we had the new version of the paper, and so my team said, let's write the paper. But my boss said, no, with the company, we're not writing papers. We now use it to invent a new material. And then we said, okay, let's find the new electrolyte for a solid-state battery, something better. And let's find that. In 1 week, we could screen 32 million candidates and then identified 500,000 potential new materials, which you have to compare to mankind only knows about 250,000 crystalline materials. So we found twice more materials than are known to mankind, and they all contain lithium. And then we found one that actually was promising. How did we do that? We started with all known crystal structures, and then we substituted atoms. If there was somewhere where an ion, a 2+, then we said, let's put in any atom that can appear in a +2 charge. That's stable, not radioactive, and not too expensive. So any of the abundant safe elements put in. Then, just by substitution, we could find about 32 million potentially new materials, of which then, when we checked the near stability, we found that about 500,000 were stable. And then we screened that to those that were insulators, because you don't want your battery to short circuit with a big band gap. Then we got to near 771, predicted by AI. Then how much do we trust AI? We didn't know, so then on the 771, we ran DFT calculations to validate it and filtered it down to 583. The ones that dropped out didn't drop out because the AI was totally off, but just because the band gap was not 3 volts that we wanted, but only 2.8 volts. And then we looked further, can we find some with fast lithium-ion transport with A again, and go down to about 74 materials. And that was the first good news, included all the known good solid-state electrolytes. So we seem to be on the right track. And then we found the 18 where we saw a path how to make it, and asked the lab whether they could make it for us. And of course they said no way, because I mean, come on. We get new proposals for materials every week, and it never works. And now you come as a software company and claim your AI can just come up with something that works. And by the way, it contains sodium and lithium that will phase separate. It will not be stable. We know it. We know it will not work. And I asked them, hey, but please make it for us. We'll pay you for it. And they made it. And then they said, wow, it works. So there's something there with AI. If it takes them 4 to 5 years to find a candidate, and with AI, the first proposal we make works, then I say there's something there in material science and chemistry that one has to understand more. So then we did the same for coolants, refrigerants, the material, but our manager pushed us not to write a paper, but ultimately, once we had that, he said, let's make it. Once we had it, he said, let's not write a paper, let's make a battery. And so we made that, and it works. To show how things are changing. Now, where does quantum come in? If you want to simulate, yeah.
Sorry, how were the original 32 million candidates found?
We looked at all possible crystalline structures that exist in a database of all known stable crystalline materials, and then we substituted atoms. Let's replace an iron atom by a copper atom by whatever. Let's replace it by elements that can appear with the same charge state. And that lithium. And that gave us then 32 million ones, out of which most were unstable, right? But 600,000 were stable, and then we filtered this down. So at that point, we had more new material, we had more than twice as many lithium-containing material candidates than all the crystalline materials known to mankind. So just there's this huge space we can explore with AI. Yeah.
Where does the 20 years number come from?
The 20 years number comes from if I were to simulate those 32 million materials with DFT on the same compute cluster, how long would it take? Instead, we screened it down to about 1,000 and ran that in a day. If we had done that on the entire data set, it would have taken 20 years. Or would have cost much more. Yeah.
Very quickly, the one new one, did that contain any completely unexpected ion? Because you said you were adding new ions.
No, so the unexpected thing was that it was a dual conductor sodium and lithium.
So
And nobody had yet found a dual ion conductor, and they said actually it would phase separate. So that was the big surprise. Nobody would ever dare look at a dual ion conductor.
And it specified the exact ratio, right?
Yeah, and so then basically we could replace most of the lithium by sodium, which is much cheaper. Yeah, so that was the main surprise. And then once it worked, once we looked at the crystal structure, then we could see the channels where the ions go through. So one could then see where, in case that's stable, how it can work. Yeah. So that was the big surprise. The experts told us, no, that can't be stable, but the AI found it. By not knowing that it shouldn't be stable. Yeah. So then these models are all trained on classical simulations, on classical DFT simulations. And the classical simulation of a quantum system of material chemical works well when what we care about is the geometry, because the nuclei are heavy, and so then a classical force field and classical simulations work well if you want the conformation, how a protein folds, for example. That works well with classical methods. If you want to go to the electronic properties, you need at least the mean field theory. DFT works well. Scaling becomes cubic. Still not too bad. Okay, but expensive already, but not too bad. If you want to understand, if you want to go beyond mean field and look at correlations, like what happens when you form a chemical bond, when you break a bond, if you want to understand the dynamics of bond formation, of bond breaking, of chemical reactions, then you have to go beyond mean field theories. The simple plus ones are the coupled cluster methods. Then the scaling becomes about the 7th power of the electron number. Now that's a bad algorithm already for practical scaling. But if you really want it accurately, you have to go to what the chemist calls full CI. You're solving the full exponential quantum many-body problem, and then the scaling is exponential. Where the quantum computer comes in is when customers asked us, can a quantum computer accelerate protein folding? I'm saying, no, it's already fast enough classically. Can it accelerate DFT? The scaling is already cubic, and it's at least cubic quantumly. It doesn't help us using a slower machine. Where quantum computing helps us is it can do the exact quantum simulation with polynomial scaling. We have it down to cubic. I think we can push it to quadratic scaling for the exact solution. So that's the big breakthrough. Can get accurate answers. So for problems that I cannot solve classically, the quantum computer can help me solve it. If I want to make things faster, that's when in the past we told people, don't come to us for quantum. Now we tell them, if you want to make it faster, use AI to learn from the classical data. AlphaFold, or what they showed on the DFT learn models for materials. To make it faster, use AI. To make it more accurate, use the quantum computer. If you want both, you combine it. So the way we now think about how we use quantum computers, because I told my team back in 2020 already, AI is coming to physics and chemistry. They said, no way. Okay, we're there now in 26, I think we know it. That's what the day is about. I told them back in 2019, 2020, we have to intercept the future where physics and chemistry will be dominated by AI. And as we build a quantum computer that's 10 years out, we shouldn't target the past, we should target the future. And so what we had in mind then is, what we're doing now is, we did, for example, the battery so much faster than with brute force classical, by taking the molecules, materials we have, we simulated them, and we had a big data pile of simulations that we used to train an AI model that can predict the result of the chemistry calculation. And then by doing the screening with the model, I can be much faster. That model is trained on the classical calculated data. The model can never be better than the training data. If the classical simulations I use, DFT, are inaccurate for chemical reactions, then the trained model will also be. So that's then where the quantum computer can come in, namely for those configurations of molecules and materials where the classical calculation is not good enough, I can do targeted quantum simulations. Do a few thousand data points on smartly chosen configurations for refinement of the model. So I can refine the model that I've pre-trained with millions of classical data points. I can refine it by giving a right set of a few thousand data points that come from a quantum computer, and then I get a quantum refined model that will be much more accurate. So it is then this quantum refined model that we're using. If DFT calculation that takes minutes are too slow and expensive for the screening of material, if I use a quantum computation that takes days, ouch, it will be even far too slow. But if I can use the quantum computer to instead create a better AI model, and then I use that AI model, then I have the best of both worlds. I have an AI model that is fast in inference, be as accurate as the quantum calculation. And that's where my friend Charlie Marcus then said, okay, Matthias, I get it. You say we need the quantum computer to teach quantum physics to an AGI. I said, yeah. You could say that that's basically deep down the value of the quantum computer. And the fact that ML models can learn correlation, meaning there's some structure in there that we as humans just don't grasp as well. But if the AI learns based on quantum data, I think that can really make a big difference here. So where will it make a difference? Everywhere where there are chemical reactions. The synthesis, making materials, making new chemicals, new drugs in a clean way, catalysis for reactions, capturing the carbon from the air, making the fertilizers in a local way and cheaper way, and the symmetry reactions, biochemistry, degradation and corrosion if you just don't have to paint your your ship or your car so often. There are many, many problems where there's a big impact. Yeah?
Can I ask you, so would this be a reasonable way to think about this? So, one could say, well, chemists had intuitions about which materials to use or which molecules to use in which circumstances. And then things got too big for them, and it was you needed to do calculations to figure out which ones are good and which ones are not. And now,
to hone the intuition.
To hone the intuition.
Yes, now with quantum computers you can hone it even better.
Right, but also maybe AI can have intuitions about larger sets than a chemist would be able to hold in their heads. Is that the premise that what you're getting from the AI is intuitions about much larger sets, but they still have to be checked against actual calculations?
Yes, still has to be checked. But if I can find a candidate that is more likely to be correct, because the intuition that the AI has is based on much more data than what any scientist can have. If AI scrape the literature and all data sets and so on, then looks for correlations. So it's also that that intuition is typically kind of a very simple model we have in mind of how things work. And then we get to computing and models there to make it a bit more quantitative, the intuition. The AI can represent much more complex models.
Yeah.
And with that, we can then do much more. So then sometimes chemists also tell me, hey, for all the work I do, classical methods are good enough, right? But that is simply because those chemists focus only on the methods where, on the molecules, the chemical space, where the methods work well enough. So we have to now think beyond what people typically do. What else could one do if I had access to a machine that has better intuition on chemistry? There's a much bigger chemical space it could explore then. So then, what's needed to get there? What's needed to get there is a machine that can simulate these molecules. These molecules have about 100 electrons. They have about 10 to the 8 coupling constants. So I have to load about at least millions of bits of data into them. So I need a machine that is stable for more than the current NISQ machines are stable for. So that's where we talk about 3 levels of quantum computing. Level 1 are the NISQ machines, the physical qubits. They are noisy, error-prone, but they showed us that actually quantum is real. We can do computations, huge impact from them. Where we need to get to is to thousands and more logical qubits that live for days. And the step in between is building machines with logical qubits, the fault-tolerant machines. And that's where we had to get to. And that's where there was huge progress in the last few years. In early 24, I want to argue there was no real logical qubit in the world yet. Because for logical qubits, I'm not talking about just memory, I'm talking about fault-tolerant computations better than physical. And then with continuum and atom, the team then showed that we can actually make logical qubits much better than physical by picking the right choice of codes. And some machines were nobody expected that we could do a logical qubit that actually succeeded. Now this year, we're shipping the first machine with 50 logical qubits to Denmark. And what is the difference between the papers from years ago is that here the team has built the entire software stack that I can address a logical qubit. I can program an ISA that has logical qubits, and where the near-fault tolerance is built into the machine. So just like on a NISQ machine I have my physical qubits, I have my gates and run them. Here I can run the logical gates in runtime with real-time feedback on logical measurements on that machine. So I have the first fault-tolerant machine with real-time feedback and logical qubits. Will that machine do the chemistry calculations? No, the clock speed is a few hertz, not my kilohertz that I want, and 50 qubits aren't enough. But it's the first step that shows we're going beyond the physical qubits. We can now build hardware and systems that operate based on logical qubits. And then we showed already 2 years back an application in chemistry when combining HPC, logical qubits, quantum AI, by saying you want to solve a simple chemistry problem. Here we did a trivial one, 2 electrons in 2 orbitals. It's a 2x2 matrix that I could solve on the whiteboard. But we solved it with HPC. We looked at the chemical reaction, a big network. We found an example that we ran on the quantum computer. And then to measure the energy of the state, we use classical shadows to learn the wave function and calculate the energy from that. And then compared to the true energy, the logical qubit number was within the error bar of the true value. If I did the same with physical qubits, it was outside the negative 2 sigma error bar. So we see that actually the logical qubits are useful. But this is just the beginning. This is the stepping stone for the future scaled machine. So I wanted to talk in the last few minutes about more, what do we need to get to a machine at scale? And one thing is I need to build an entire computer. And the good news is quantum computers are computers, and we know and have known for decades how to build computers. The one thing that quantum physicists who always like to reinvent the wheel, including me, the one thing what we have to learn is people have worked for decades in building computers, and we can learn from that. It's the same stack from the workloads, developer tools, the cloud services, the cloud data center layer, that we call in Azure, to the hardware. It's the same stack. And as we zoom into it, it's the same stack. How do we run the workloads was a question. How will we use a quantum computer? Well, we'll use a quantum computer just how we use a classical computer. How is that? I'm typing into my Copilot, my chatbot, do this calculation for me, and it works. So using computers has changed to AI. We'll use computers in the same way. The workloads are based on AI models, applications, libraries, and so on. It's the same thing. The quantum computer will just give you, ultimately, it's the same stack. We just add another type of compute cluster to our data center. For the rest of the stack, we're building just yet another type of computer. That helps us because we need people to build it. There are many engineers who know how to build computers. We just need the help. The other question is, how can a quantum computer be programmed? That's what people asked, and that's also what our company leaders ask. Where do we find the people who know how to program a quantum computer? And the answer back then, and that has now been realized, was, of course, AI will program it. Since we have our development tools where you can take a circuit, you paste it into Copilot, and Copilot then implements it. And then you can tell it, now run it. Or we even can say, look, there have been all these new advances on Shor's algorithm. Can you just take those math papers and turn it into code? It works and it works. So you can actually take quantum algorithms papers and use encoding agents you can these days turn the papers and the math into quantum programs that run. So that's a big step for us, that it's easy to turning a quantum algorithm, Matthias, into working code with AI. The people told me it might not work because quantum is so different, but ultimately it's all about translating between the algorithm description and the math of it to a program, and that's the same whether it's a classical algorithm or quantum. So the AI can help us a lot with quantum coding, and so I think that any theorist and then the application scientist cannot just turn quantum papers into code. But so where's the real challenge if the quantum computer is just another machine we're building and the program is done by AI? I think the real challenges are two. One challenge is coming up with new quantum algorithms with quartic speed or more. That is still a big challenge, more applications. The other one is really building the system at scale. And that's where I want to walk you through a discussion of where I believe the biggest problem is. For that, we have to start with quantum resource estimation. I have to estimate how many qubits I need and what is the runtime and so on. And that is just a fancy name for what the classical person calls a profiler. I use a gprof tool to run my code through it and get a profile where it is. Where the classical architect has an architecture simulator that gives us memory use and runtime. Similarly, QAE just gives us the same. It simulates the execution on certain hardware, and it gives us the runtime needed and the qubit count. And the stack we go through from the code down to the signals is very similar to the classical stack. I go from a program, I compile it to an intermediate representation, to an executable that uses an instruction set architecture that then is mapped within the QPU or CPU to microcode that is then executed with control signals sent to transistors or qubits. We can map it to the same system architecture of a classical computer. That helps us because it helps us get the right abstractions in place. And I've often had the physicists tell me quantum computers are very different than classical ones because the program has to know about the physical qubits. I said, I don't think so, because even for classical computers, we're changing the microarchitecture of CPUs while keeping the rest of the stack the same, and your program still run after 20 years because we have the right abstraction layers. We need the same for quantum. So the challenge is more in the scale. And let me now say it might take about 1,000 logical qubits to run such a chemistry problem. You can change numbers in there if you want to. These 1,000 logical qubits, there might be slow ones or fast ones. So the clock speed might be between the kilohertz and the 100 kilohertz. To keep the cost low, I need those 10 microsecond cycle time. I need the 100 kilohertz target. You then think, what does that mean? I'm issuing instructions on up to 1,000 qubits every few microseconds. So getting between 10,000 and 10 million instructions per second. That's something that's not a big deal. I think you can do that in software. Then I go deeper. Okay, so, and I might have a few measurements. Then I go deeper and turn that into really the quantum instructions, when now I'm really doing one operation per logical qubit per cycle. When I don't need it, then at least have to correct the errors. Now I'm doing about 10 to the 6 to 10 to the 8 instructions per second. It gets a bit more challenging, but the bigger challenge is when I'm using a code like a surface code or similar, or I'm just doing measurements. In the surface code, the native instruction set are measurements and joint measurements. So now I'm getting between 10 to the 5 and 10 to the 8 measurement results per second back. And now if the compiler translates every unit operation like a control not operation on a sequence of measurements within Celas, that means every control not operation now gives him back 4 bits in measurement results that I have to process for polyframe tracking. That's where it gets really challenging. So I'm saying I want my instruction set architecture not at the operations of my code, but I want it higher up at the unitary gates, and that should all be done by the hardware. But then I'm going down further, and now what is the overhead? The overhead is in space-time between a factor of 1,000 and 100,000, so let's assume that. And I'm getting to between 10 to the 9 and 10 to the 13 physical qubit instructions per second. I'm seeing many papers that say the compiler compiles it down and then we issue 10 to the 13 instructions per second. I think anybody who's written a computer program knows that may be hard. So this is something down there that I think we have to harden. We have to build control hardware here to really harden the mapping from logical to physical qubits, or it will just become too expensive. So that's where we need to think about, how do we build the computer, how do we build the control hardware to do that mapping from logical to physical qubit in the hardware. Again, just like in classical computers where we have specialized units, like for floating point arithmetic, not because they can't do it in software, but because it's just too expensive and slow in software. So we'll have to actually work lots on how do we harden the control. And then same on the way up, I have to measure 10 to the 13 measurements a second. So let's assume now a fast quantum computer, cryogenic, and I'm doing the control. The control, I'm sending 10 to the 13 instructions per second down. If I just blast that down, if I could it would heat up my qubits and they would boil. So I need to put that to cryogenic control. Readout, similarly, I have to measure up to 10 to the 13 measurements a second. Readout, I'm more optimistic because the way I can do that is I can multiplex it in frequency space and free space, where I can bring out the analog readout signal to room temperature, multiplexed in fewer lines. So with a few thousand lines, or with some free space optics for certain qubit types, I can bring things out and then process it at room temperature. And that I think is doable. It's an engineering challenge, but it's doable. The bigger challenge is the control, right? Have these 10 to the 13 physical operations a second, sending it down at 10 bits per instruction, 100 terabits a second, no way. We have to really do the mapping in the code. But how do we do it? Let's say we have 10 to the 12 control pulses per second. And for a cryogenic qubit, at millikelvin temperature, can dissipate about 1 milliwatt. That means per operations, I have about a femtojoule. And it takes a few femtojoules to switch a transistor. There is a simple engineering problem for the scalable control. You cannot do it by saying, let's split it out over hundreds of cryostats. Okay, then the cost will go up a factor 100. So we've always thought about what is really the solution to that problem. And that's where we already 20 years ago picked the topological qubit for the wrong reason. The reason why we picked it because we thought it has this amazing topological protection that reduces the overhead for quantum error correction. But there's more, namely, really, in the meantime, I see the real advantage is the scalable control. So I have it by chance, have something with me. I have the Majorana 2 device here with me. On this size, we could, in the end, place about 1 million qubits. Right now, we have 4 on there. But the same size could scale to 1 million with the control all together. So how is that possible? It's possible by starting from, by saying I want to actually do a qubit that is in a topological phase of matter, that implements the same TQFT that I'm using in the surface code. So I'm implementing my topological phase of matter, my topological code in hardware. I do that by starting from aluminum, which when I cool it down, becomes a superconductor. And then I proximatize it with the semiconductor to have a phase in there that combines the properties of the topological semiconductor and the superconductor to make a topological semiconductor. And in order to make it real, the interfaces have to be atomically perfect. This is not computer graphics. This is an actual microscope image. You need to make these perfect interfaces. Once that is done, then we take this wire, we apply a magnetic field along it that closes the trivial phase and then reopens the new topological phase of matter. And I tune into that with the right voltage. When I do that right, then at the end of the wire that's a few microns long, so 1,000 times 1,000 is that small, that's where I get the circular modes. They are the Ising anions. I can use them for computing. The simplest thing is if I take 2 of them and I combine them, those 2 Majorana's can either form an electron, that's the one state, or the 2, when I fuse those 2 anions, I can combine them and form a 0. So with that, what do I have? I have a wire that's a classical bit, because the total charge is conserved. If the total charge is even, then all the electrons are paired. Those 2 particles form a 0. If the total charge is odd, it's a 1. It's a classical bit. Now I take 2 wires. 2 wires, the total charge is conserved. Let's say the total charge is even. It can be 0, 0, or 1, 1. Those are the 2 states of my qubits. What do I have to do is I have to do measurements. If I measure between here and here, I bring those 2 together and measure that to measure the classical bit. So here, if I measure this and this, that is a C measurement. Now the magic of Majorana's come in. If I measure those 2 vertically stacked, it's an X measurement. If I measure the 2 across, it's a Y measurement. If I take 2 qubits and measure between them, I can do an XX measurement, CC measurement. I can do all the Pauli measurement just through measurements. I can do all my Clifford gates through measurements. And we've shown that we can actually take the wire, and when we tune it into the topological phase, then we see 2 states that we measure, well separated. So we can measure it. And where does the magic then come in for control? If I'm implementing, let's say, a surface code, I can do the syndrome extraction in the surface code, can map it to 1 and 2 qubit Pauli measurements. It's a sequence of 4 steps where I'm doing X, C, XX, and CZ measurements. And if I do that in the right pattern, then I'm getting all the syndrome measurements for the surface code just through measurements. Now the magic for control is measurements don't need fine-tuning. A standard X measurement would mean I apply a Hadamard gate. I have to rotate exactly by 90 degrees. Here I can just do the X measurement natively by picking the right Majoranas. I can do everything with measurements. What I have to do after the measurement, I have to turn it off. I just have to apply a large enough voltage, no fine-tuning needed. For the timing, I can just clock it. If I measure for a microsecond or 2 microseconds, doesn't matter, it's a measurement. I can use an external global clock for the timing. The voltages can just be rectangular digital voltage pulses. And fine-tuning of the qubit, I just need to bring it into the phase, not to a specific point. So the fact that the qubits in here, they are in a topological phase, that makes the control easy. Because I can basically control the Majorana qubits with digital control pulses. I can control it with transistors. That's why I like the topological qubit, just because it has this path to scale in the control. That the math behind it, the topological phase behind it, really helps me solve the control problem. With that, we then have a path to utility scale, and it will really change the way we do chemistry. Thank you.
Oh, thank you so much for going over everything. I would say like
I skipped a few layers, but almost, yes.
So that's why that's one of the questions I had. I mean, you mentioned AI, you also mentioned ML. I know you've written a lot about RL as a specific method. Are you talking about RL being used for chemistry, or LLMs, or both, or something else?
All of it. What we first had the question was, so first we trained specialized models that learned the force fields, for example. Then the question from our Nigeria CEO was, if we invested so much in OpenAI and build the data centers for the LLMs, can't an LLM do it all? Why do we build our own specialized models? Like we had a model for image recognition, we had a model for translation and so on, and we all replaced them by language models. Why do we still do models for materials? And then we showed that if you just put in the molecular structure, the equation, it doesn't learn it, it can't learn it. You need more of it. You need the proximity, you need the geometry, you need more. And so we showed that for certain properties, it works perfectly well. Whether something is soluble, perfect, it works. Because it's more about what are the atoms in there, is it polar or not, so easy. But when you want to look at the gaps, the quantitative numbers, it never learned. It was worse than random guessing even. So we need specialized model architectures that capture the right features. Simply because the training data set sizes of a few millions, they aren't large enough. If I had trillions of data points from chemistry, then maybe yes. But when you have fewer data points, there's always the way to substitute for that with inductive bias in the model architecture. So because we have few data points, we do that. And then how we train it, that is with RL as well. But we need specialized models so far that we then combine with the language models to orchestrate the work. And then this chip, how we made it quickly is just using RL and AI in the chip design. How do we build the software stack for Marken in Denmark with a small team? By basically me telling my team, stop writing code, have AI agents do the code, and you just manage the agents. So in that way, we can build more components and subsystems than we have people on the team. So it really accelerates the way we do the work.
So, how fast is the measurement? Right at the end, you were talking about. I've got a couple of questions about that.
Microseconds.
Okay, and also, can you change the axis of the measurement continuously, or you
No.
strict? You can't.
We can't, and that's a feature.
Well, okay, depends what the application is.
Okay, so you see, let me go back here. When I do these two, it's a C measurement, that's the X, that's the Y. Those are the measurements I need for QEC.
Yeah, and I'm thinking about different applications.
Then I may also need rotation, so I need a T gate in addition. Right? So, but then So we need the protocol cultivation, distillation, and so on to then make better the non-Clifford resource states. Those protocols are all implemented through Clifford gates. So it's all the initial non-Clifford that you feed in. And that's where it turns out that what counts for the output quality of the distilled magic state, the biggest knob you have to improve that is the 2-qubit Clifford fidelity. Not the initial non-Clifford resource state. That can be noisy at 95%. It's good enough. The important thing for the distillation is the quality of the Cliffords.
Back to the measurement. Can you also, you said it takes a microsecond. Can you make a sort of a shorter measurement and get a generalized measurement in a controllable manner?
Yeah,
you get a weak measurement in a controllable manner?
I don't want to do a weak measurement, but what I actually want to do for the T-states, for example, I want to couple it to the reader dot and then want it to the phase.
Right, but is it in principle possible to get a controllable weak measurement?
Likely, yes.
Yeah. Measurement-driven quantum computation, where you actually drive everything with weak measurement. Different models.
This is different. Here I'm implementing the Clifford gates
I know,
through measurements. Yes.
Maybe we can take the rest of the questions offline. Thank Matthias for